Now in chapter 6, we're going to do partial derivatives. Partial differentiation as a whole there's more busy work than other branches of advanced mathematics, but it can come in handy in certain, especially in applied fields. The meaning of partial derivative just means that you will, for example, if you have a function that has two variables, you will pretend all the other variables, two or more, you will pretend the other variables to be constant and take the derivative only with x. That is, the others are all constants. You just take a derivative of part of the formula. What that means you end up doing is that you have, this is a surface in the three-dimensional space. So you have a surface and you're pretending you're just taking a plane and cutting the surface, intersect the plane with the surface so that you come up with some kind of a curve. And the partial derivative is the slope along that particular curve. Now, if you can, your book will probably show you some complicated looking pictures. And as you read along, you might or might not be able to visualize it. If you can visualize it, that is great, of course. But if you can't, it doesn't make that much difference, because it all comes down to just the formulas. You follow the formulas and calculate everything, okay, regardless of whether you can see it in your mind's eye or not. Now, as an example of taking a partial derivative, for example, let's say we have an equation that says x squared, y squared, z squared. So let's say we have an example, y squared, z squared, and they have certain things on the bottom, 16, 12, 9, 12, and 9. So let's say if you're asked to figure out what is partial z over partial x. So this is the delta sign. Partial x equals to, you just take it, everything is with respect to x, where c is the dependent variable in this formula. Okay, c equals to fxy. Now looking at it in that way, we will have, you take derivative of this thing will become 2x over 16, okay, plus the derivative of y is just going to be 0, because remember, y is constant, because that's what you're holding. And then c is becomes 2c over 9. And since c is the dependent variable, you get partial c over partial x. And that is actually that shouldn't be here, because this is an implicit function. So this, and you just take everything with respect to x. Okay. So then, and then one's derivative, one being a constant, is 0. Right now, remember, y is also considered a constant for this job. So then you have something like this with partial c, partial x in there, and you just do some algebraic manipulation to come up with 2x over 16 divided by 2c over 9, or times the opposite, is equals, and this whole thing is negative, and that will be equal to partial c over partial x. Now this is not 2. Yes, it is 2. Anyway, so that's it. And then you clean that up a little bit, and that should come up with something. And of course, this particular solution has c right inside the equation of partial c, has c itself. You can leave it like this, but sometimes your professor might require you to solve for c and plug it in, so that everything is in terms of x and y only, which is fine. But anyway, that's how you do partial derivatives. Is no harder than just ordinary derivatives, even though people often, math majors often consider partial derivatives harder. It's not harder, it's just, well, longer, because you have these various parts, so you have to get it all you have to do everything multiple times to get it to come out. But anyway, let's move on. Now we'll consider the tangent of a point. Suppose you have a surface and you want to have a tangent plane at that surface. For example, let's consider my rock here. Okay, let's say that this rock is smooth right here. So you can imagine the plane like like this thing. Okay, that's tangent to the surface. Now, how do you calculate the equation of that plane? The way you do it is it has to do with the partial derivatives, and the way it comes out is like this. The partial derivative is, well, first we will give a quick definition. This is a shorthand. That is f1 AB, f1 xy is the same as partial f over partial x, and then similarly f2 is xy is the partial with respect to y, partial f and partial y. So that's just another way of writing the same thing. Well, some people think that looks neater. In any case, the formula for the plane tangent to a surface, you have a surface S, and you want a plane that's tangent to it at a specific point that's called ABC. So the formula of a plane tangent to the surface S at ABC is this particular formula, which is this plane is called Z equals to FAB. And then F1, that's the constant, F1AB times x minus 8 plus F2AB times x minus b. And in fact, this is equal to c, okay? So anyway, that is the formula of the plane. So the partial derivative, once you calculate it, you will be able to calculate the tangent of the tangent formula of the plane, the tangent plane that is the plane that is tangent to S at the point ABC. And that's one use of the partial differential equation. How this thing comes about has to do with some of the basic, more elementary math. But if you can't remember this kind of stuff, the elementary formula of plane surfaces, it's not that important. Just remember this formula, and that's how you're gonna calculate the results. And then another thing is we have the line that's normal. Okay, a normal is often used to define the line, that is to show the direction where the plane is going. If you have a plane in the space, you know, my hand is the plane, or maybe better yet, I should use this thing. Let's say this is the plane, and the normal is the direction arrow, which shows which way the plane goes. It doesn't show where the plane is, but it shows which way the plane turns. See, so the formula of the normal from more elementary math is given as from this number is given as the ratio. There's a ratio to this normal. F1. The ratio is F1A comma B to F2A comma B to 1. That pardon me, negative 1, and that is the normal. And this particular normal, it just means how much, if you draw, say, something in 3D, okay, let's say this is C-axis, X, Y, C, or something. But anyway, so you have something pointing out, okay, is particular amount that as it drops down to the 3 axes, the shadow it casts, the perpendicular distance here, these things, positive or negative, is called the directional values. That once you have these 3 values, you know how far how far to go out from X, Y, and Z, then you know which way your arrow is pointing, which then shows you which way the plane is going. But that is from more elementary math. If you don't remember, it's not important. Just memorize this. That's how you do in math. Eventually, you forget some of the easier stuff, but you can still continue to do it. Remembering it is not necessarily important. And that marks the end of our first lecture. And in the next lecture, I guess we will do a couple of very easy examples. Like I said, partial derivatives has a lot to do with just doing a lot of basic algebra.